Hello dear students, welcome you all for Power System Operation and Control class. So continue with the third module. In that we have seen the previous class tie line control with primary speed control. We have seen the two areas how connected with the tie line and its block diagram we have seen. And at the same time we have seen the change of the load in area 1 is seen. Today we will see change of load in area 2. Now consider a change of delta PL2 in the load of area 2. So we can get the relationship like this, that is delta PM1 is equal minus delta PL2 is equal to delta omega D1. You can make the correction there, that is delta PM1 minus delta PL2. Okay. Now next is delta PM2 plus delta P12 minus delta PL2 is equal to delta omega D2. So using the previous equations we can write minus delta PL2 is equal to delta omega into D1 plus 1 over R1 and delta P12 minus delta PL2 is equal to delta omega into D2 plus 1 over R2. So we are having these two equations of 17 and 18. Okay. Adding the equation 16 and 17 we can get that delta omega is equal to, because after adding the equations here only delta omega is remains here. That's what delta omega is equal to minus delta PL2 divided by beta 1 plus beta 2, because we have seen what exactly the beta 1 and beta 2 in the previous classes. Beta 1 and beta 2 are the composite frequency response characteristics of the area 1 and area 2. Okay. Now so equation 17 we can write it as delta P12 is equal to delta PL2 beta 1 by beta 1 plus beta 2 is equal to minus delta P21. So that is the changes. Anyhow you are knowing 1 2 is in change in first area to second area, means obviously the reverse order is taken place in second to first area. That is, if it is increases in first area, obviously decreases in second area, or increases in second area means decreases in the first area. So this is regarding the change of the load in area 2. Okay. Now we will see change of load in both areas. Okay. So here if we have a simultaneous change in the both the load areas, we are going to get delta PM1 minus delta P12 minus delta PL1 is equal to delta omega D1, and delta PM2 plus delta P12 minus delta PL2 is equal to delta omega 2. So 21 and 22 are the two equations we get. After adding these two, we will get that minus delta P1 minus delta PL2 is equal to delta omega D1 minus delta PM1 plus delta omega D2 minus delta PM2. Or by simplifying that one, delta omega into D1 plus 1 over R1 plus delta omega into D2 plus 1 over R2. These things are nothing but beta 1 and beta 2. So we can write it as delta omega is into beta 1 plus beta 2, where delta omega can be written as minus of delta PL1 plus delta PL2 divided by B1 plus beta 1 plus beta 2. So now delta P12 is equal to minus delta PL1 beta 2 divided by beta 1 plus beta 2 plus delta PL2 beta 1 divided by beta 1 plus beta 2. Then 1 over beta 1 plus beta 2 is taken as common. We can write that is 1 over beta 1 plus beta 2 into minus of delta PL1 beta 2 plus delta PL2 beta 1. So we can observe from the above discussion that only primary governor control load change in either of the areas will lead to a steady state deviation in frequency of the both areas. So we will see one problem now, then we will go to next part, that is tie line bias control. Before going to the tie line bias control, we will see one problem first. Yeah, consider the problem 7.1. Here two control areas are connected via tie line with the following characteristics. Area 1 is given that R1 is equal to 1%, D1 is 0.8, base MVA is 500. Area 2 is R2 is 2%, D2 is 1% and base MVA is 500. A load increase of 100 megawatt occurs in area 1. What is the new steady state frequency and the change in the tie line flow if the nominal frequency is 50 Hz? Repeat the load change occurs in the area 2. So first one is when the load change occurs in area 1. So the data are given here, everything. So we will directly move to the problem. First is when the load change occurs in the area 1, then the equations we are knowing that delta omega is equal to minus delta PL2 divided by beta 1 plus beta 2. Here what is delta PL1? Delta PL1 is nothing but 100. Is it given? There change load increase of 100 megawatt is given. So obviously change is 100 megawatt. But on the base of 500 MVA, so we are dividing it by 500. We will get 0.2 per unit is the delta PL1. Beta 1 we are knowing 1 over R1 plus D1. That is 1 over 0.01 plus 0.8, that is around 100.8, and beta 2 is obviously that is 1 over R2 plus D2, that is 1 over 0.02 plus 1, that is 51 we are going to get. So once we got the beta 1 and beta 2, we need to calculate the delta omega. So putting all these values, whatever calculated beta 1, beta 2 and delta PL1, we are going to get delta omega as minus here 1.3175 into 10 raised to minus 3 per unit. That is the frequency deviation. So if you want to get it in the actual hertz, that is delta omega is converted as delta f by multiplying the actual frequency 50. So actually it is given in per unit value. If you multiply it by 50 actual frequency, you will get the hertz. That is minus 0.065875 hertz as the delta f, that is change in frequency. So new frequency is 50 minus the change. So we will get 49.93415. Actually that is and frequency plus delta f value we got it in minus, so obviously it is become 49.934125 hertz, or we can directly write it as approximately it is 49.93 hertz, or delta PL2 is given by minus of delta PL1 beta 2 by beta 1 plus beta 2. We are knowing by putting all these values we will get that minus 0.0671936 per unit, and if you multiply it by the 500 base, actually it is in per unit value on the base of 500 MV, if you multiply by 500 we will get minus 33.597 megawatt. So there is a drop in the tie line flow. So when we balance the changes as follows now, the change in generation area 1, that is delta PM1 is given by minus delta omega by R1. So if you put that one values here, minus of minus 1.3175 into 10 raised to minus 3 divided by 1.01, we will get 0.13175 per unit, and multiply it into the base, we will get the 65.875 megawatt. So increase in the generation since a positive value, and change in the area 2 is given by same delta PM2 is equal to minus delta omega by R2. We are going to get 0.06585, that is multiplied by 500 we will get the 32.9375 megawatt. So increase in the load area 1 is equal to 100 megawatt. So change in the load area 1 due to the drop of frequency is given by minus 0.527 megawatt, and change in the load area due to the drop in frequency is given by minus 0.65875, because the equations we are knowing that delta omega d1 and delta omega d2. So change in the generation is addition of the 1 and 2, that is the change in area 1, generation area 1, generation area 2, we will get 98.8125 megawatt. Change in load is nothing but 3 plus 4 plus 5, that is increase in load area, change in load area 1 due to frequency drop in frequency, change in load area 2 due to drop in frequency, we will get 98.81. So change in generation is equal to change in the load. Delta P12 is being negative, means there is a flow of 33.597 megawatt from area 2 to area 1. Out of this 32.9375 megawatt comes from the increased generation in area 2, and 0.65875 megawatt from the drop in the area in the load area 2. So this is regarding the first case. When the load changes occur in area 2, then the same thing, delta omega is equal to minus delta PL2 by beta 1 plus beta 2. If you write all those values, we will get minus 1.3175 10 raised to minus 3 per unit, or by multiplying it by 15 we will get minus 0.0687 hertz, or actual frequency that is 50 minus these values, we will get 49.93. So delta PL2 we are going to get 66.4 megawatt. So there is an increase in tie line area, tie line from area 1 to 2 to meet the increase in the load area 2. The increase in tie line is met by increase in generation area 1 by 65.875 megawatt, and decrease in load of area 1 by 0.527 megawatt. So this is what the problem, how the changes in the area load changes in the area 1 and 2, how it affects on the generation and all. Okay, So if you find any difficulties, you can ask me. So in the next class, we will see the tie line bias, all those things. So this problem is very easiest one. And anyhow, the second problem is that is a Simulink model is given. If you want to that one, you can see the example 7.2 also. From there you can get the few ideas on this one. So they are done with the Simulink model to solve this problem. Okay, so first problem you have to solve by your own once again. Okay, in the next class we will see the tie line bias control, that is frequency bias tie line control. Okay, thank you.